speaker is Shruti Murli from IMSC Chennai. She is going to talk about subfactors associated to Latin squares. Please go ahead.
Good evening to all. And first of all, let me thank the organizers for giving me an opportunity to deliver a talk here. This is my recent work with Professor Vijay Kodialam. So I wish to talk on, as the title says, subfactors associated to Latin squares, or equivalently, subfactor planar algebras associated to Latin squares. So before getting into the details, let me briefly give the definition of planar algebra. As my time is very limited, I'm not getting into a very elaborated definition. Let me briefly define it. Okay, so before defining planar algebra, let me define what is a shaded planar tangle. So a shaded planar tangle is the data of, it has finitely many input boxes. As this example I have shown the right side. So finitely many input boxes, and there is one output box, and there are non-intersecting strings, which gives an even number of marked points or marked intervals for each boxes, internal boxes as well as external boxes. So so it has an even number of marked points for each boxes. Out of this interval, so if this has an even number of intervals, out of this interval we will choose one as distinguished one, and we will place a star mark near to it. And the next data is there is a checkerboard shading of the region of the tangle. And finally, associated to each box, there is a pair n epsilon, which is called as color, where that n corresponds to the half the number of the marked points, and that epsilon is plus minus accordingly as the star marked interval, whether it lies in a white region or a black region. So for example, if you see that this D1, it has 6 marked points, and the star marked interval lies in a white region, so its color is 3+, like for others also. And the n can be very well be 0. For example, D3 and D5, it has 0 marked points, so n can be 0 also. Now we say the color of a tangle means color of the external box. So for this current example, the external box has 8 marked points, and the star marked region lies in a white region. So white interval lies in a white region. So is a 4+ tangle. Now let me define what is a planar algebra. So a planar algebra is a family of vector spaces indexed by the colors, which we say as n box spaces, on which the planar tangle act as multilinear maps. So for the above example, so usually we denote the tangle by T and the multilinear map by Z subscript T. So ZT, it is a map from this space to T4+. Okay. Now the following proposition, it gives the basic structure of the planar algebra. So let P be a planar algebra. Then for each color k plus minus, the vector space, it has the natural structure of an associative unital algebra. Okay. Now let me define one important class of tangles, which are called rotation tangles. So for each k, we have the rotation tangle R. So this notation actually means the subscript shows the colors of the input boxes, and the superscript shows the color of the external box. So here, this is a rotation tangle. It has only one internal box of color k plus and one external, and of course, external box of color k minus. And the map ZR, it maps pk plus to pk minus. Okay. Now let me give some definitions which we need later. So what is an Adamant matrix? So some definition which I will give are, these are just terminologies, are objects which occur in quantum information theory, quantum coding and all. So what is an Adamant matrix? An n by n complex matrix is said to be a complex Adamant matrix if the condition holds. Okay. So the following is an example. Let omega be a primitive nth root of unity. The matrix given below is a complex Adamant matrix, which is a multiple of the so-called Fourier matrix. Now let me define what is a Latin square. So a Latin square is an n by n array filled with n different symbols, each occurring exactly once in each row and each column. So the obvious example which will come to our mind is the group table of a finite group. So the multiplication table of a finite group is a Latin square. Now, there is a classification result for Latin squares. I'm not getting into any of those details, but according to that classification, up to order 4, there is nothing other than group table. All of them are equivalent to groups. Only the non-trivial example, it occurs in size 5, and it is given below. And this was the main motivation for us to do this work actually. So we mainly explicitly computed the factors for this, and this motivated us to do the general situation. Okay. Now let me define what is a quantum Latin square. A quantum Latin square of size n is an n by n matrix of vectors in Cn such that each row and each column is an orthonormal basis for Cn. So the easiest way to get is from any Latin square. If you take any Latin square, you will get a quantum Latin square just by taking the standard orthonormal basis for Cn. For the example here, if you just replace the numbers by EIs, then you will get a quantum Latin square. So any Latin square gives a quantum Latin square. But not all quantum Latin squares arises in this way. So the non-trivial examples can be found in. I will give the references later. Okay. Now, let me define the important object of this talk is a biunitary element. So let P be a star planar algebra. So star planar algebra, just for a while, I'm not getting into more details. It just means that each pk plus minus has a star structure. Each space has a star structure. Of course, it has to satisfy some compatibility with Tankel action. So now we need only it has a star structure, and U is an element in pk plus. Then U is said to be a 0,1 biunitary element if the elements U and the ZR, as I said earlier, ZR maps pk plus to pk minus, they both are unitary elements. Now, let P be the well-known spin planar algebra, which is well-known from the John Pfundt's first paper on planar algebra itself, and he has shown that it's it can be described as the planar algebra of the following bipartite graph. We don't need any of these details, so I'm not going to more details. So unless otherwise mentioned, P will always, throughout this talk, P will be spin planar algebra. Okay. So the main motivation for us to do this Latin square case was already it was shown by Von Jones in his fundamental paper on planar algebras that Adamant matrices, it corresponds to 0,1 biunitary elements in P2 plus, and there are subfactors associated to these biunitary elements, which motivated us to do the higher case too, the Latin square case. Okay, so let me have some notations. Let LB, throughout this talk, L be a Latin square, n by n Latin square, and we saw earlier that it gives a n by n quantum Latin square. So analogous to the above description, we have the correspondence for quantum Latin squares. So this is our previous work, myself, Vijay and Sundar, our previous work, and this is one among the main theorem in the paper. So this is an analogous correspondence for quantum Latin squares. There is a natural 1-1 correspondence between 0,1 biunitary elements in P3 plus and quantum Latin squares of size n by n. Okay. Now, so the same paper which I mentioned earlier, the main result is the construction of subfactors from biunitary elements by constructing appropriate subfactor planar algebras. Actually, in fact, we have done in a more general, not sticking to spin. It's a general setting we have done, but for our context, we need only spin case. So let P be the spin planar algebra and U belongs to pk plus BA 0,1 biunitary element. Then corresponding to U, there is a subfactor planar algebra, subalgebra, Q of P. So we can construct, using this U, we can construct a planar subalgebra Q of P. So this construction, it surprisingly yields plenty of subfactor planar algebras from the spin, even though spin is not a subfactor planar algebra. Okay. So we are in the following situation. So we have given any Latin square, I mentioned earlier, we will get a quantum Latin square. Using a quantum Latin square, you will get a 0,1 biunitary element. And given a 0,1 biunitary element, you can construct a subfactor planar algebra, which is the sub of the spin planar algebra. This planar algebra, this planar algebra, we are trying to analyze. And our main result of this paper, it shows that the subfactor planar algebra associated to a Latin square. It is the subgroup group planar algebra. So this is from Wade's paper on subgroup group planar algebra associated to the subfactor Rg in Rh. where the main content is that this subgroup group pair H and G is calculated from the Latin square. Explicitly, you can calculate the pair H and G from the Latin square, and it is just an algebraic calculations. Okay, let me state the theorem more precisely. So let L be an n by n Latin square and Q be the associated subfactor planar algebra, where Q is a sub of the spin. Then there is a subgroup group pair H and G of the symmetric group Sn, such that the index of H in G is n and Q is isomorphic. Not even isomorphic, it is in fact equal, because the Wade's paper on which I cited here, the main result of that paper is that the subgroup group planar algebra associated to this subfactor Rg in Rh, it is the invariant planar algebra for the action of G on the spin. So that also comes as a sub of the spin, and our construction of this Q, that is also a sub of the spin, and we have shown that they are in fact equal. Yeah, that's all this. Thank you.
Thank you for such a nice lecture.